kids also have like Zoom elementary school or whatever. That's wow. I see.
Right now it's hybrid for us. So this is a remote learning. You guys all look reclined and comfortable. All right. Hi, everybody. Sorry for the change according to from the schedule. Actually, I meant to update the schedule this morning and I forgot again. But here's roughly what happened: is Terry and I were talking late last week, and we sort of had this conversation where, you know, we both think that manipulation is a lot more than pick and place. But we've been doing a lot of pick and place, and it kind of, you know, it was enough of a conversation that it made me want to not do pick and place this time and try to do a little bit more that's going to show you the breadth of manipulation. Even though we're going to build up more and more tools, I think for perception of objects that you might just pick and then place, let's take a little break and make sure you know how to apply force. So there's a bunch of different things to do in this space, but there was another thing that made me sort of switch here, and it was kind of staring me in the face from the last lecture. You know, this is of the data set I generated. I'm sure you noticed it, but this is scenario number 9,954. And it's just, you know, I'm looking at this, and actually there was two reasons why it was notable. First of all, the mask-R-CNN network, even on the bigger data set, identified everything on the right perfectly and somehow missed the Cheez-It box. You know, how do you miss the Cheez-It box when it's But okay, but it missed the Cheez-It box. So that was the reason I stopped and paused it and thought about this one. But then thinking about it again, I was thinking, we have no way. I have given you nothing for picking up that Cheez-It box. That Cheez-It box is flat on the ground. You've got a big gripper. How are you going to pick that up? There's no antipodal grasp. I mean, our strategy will not do the wrong thing, right? It'll just not ever return grasps of any reasonable, it will never find pairs in particular. So if you think about what would happen, right? Since I'm going to find, if I sampled points on the boundary of the Cheez-It box, it's going to align the hand normal to that. And then it's going to place the other finger inside the box. So it's going to say it's in collision, and it will simply never return a viable grasp on the Cheez-It box. You could imagine a different strategy that might find trying to grab the corner of the box, and then maybe the lack of antipodalness would make it a bad grasp, but it might eventually try. The one we wrote up last time would not even try. And even if it did try, it probably would fail. This is a case that would be very hard with our gripper. So I asked my daughter, like I said, it's a remote week. I asked my daughter, first of all, she totally cheated. I thought I found a 2-finger gripper that was like sufficiently small, but she found a way to make it open up even more. And I said, hold on a second, no, put it back, don't do that. Pretend you couldn't have done that, try again. And then she does this, which is not what I expected, and was way more clever, because then it was too tall for the box, so she could just grab it the easy way again. So after I sort of narrowed the domain well enough to roughly what I thought she should have done, we started doing things like that. Okay, and then I said, okay, use your hand, and okay, that's way easier if you have a dexterous hand, and her hand's big enough too, and if you stop and watch how you go through the world and pick things up, it is not anything like what we've been talking about in class, right? This idea that you're going to look at the geometry, decide on a grasp based on the ability to maintain a slip-free grasp during the entire motion of your hand, and that you're going to place it down exactly in the same relative configuration relative to your hand as you set it up. That's just not how humans manipulate things. So it's tempting, and it's an easy thing to program, so we do it a lot. But I'd say if you look at like how robots manipulate things and how people manipulate things, there's a huge difference, right? I was having fun with it, so I asked her, this was actually last year, I asked her to start flipping some carrots or whatever, and I tried to draw on top of it just so you could see if we pretended it was a rigid thing. Oh, that's cool. So yeah, people don't, what I want you to observe here is that her fingers are sliding constantly along that motion. This idea that we should like think about the friction cone, stay in the friction cone, that's a good idea, but it's okay to slide too. And actually, probably most of the time when you're manipulating things in your home and the like, you are not in a static friction condition, you're in a more sliding friction, and that's just okay, and we're good at that. So I wanted to stop and talk today about a little bit more about what just kind of the first steps towards thinking more about the general class of manipulation. Now, the example that I coerced my daughter into of pushing the box against the wall and then sliding it up, you would call that a non-prehensile manipulation. That's what Alberto's lab would call it for sure. And it roughly, the word prehensile means grasping manipulation, and non-prehensile means non-grasping manipulation. And you'll see that word coming up. And this is, the force control is not synonymous with non-prehensile, but as you start getting into more strategies that don't involve force closure grasps, then you start thinking about things like forces. So we're going to talk about force control today. This is actually an early example from Jiaji Zhu, and Siwan Feng, who were hanging out at TRI one summer, and we're thinking about a couple of things about force control, but also about planning under uncertainty. And that's actually Matt Mason's book, good manipulation book. And I really like, there's a lot of things going on in this video. But picking up a thing that's too big for your hand, it opens up a lot of interesting topics. So Okay, let's step through a couple of the clever ideas in that. So first of all, pushing down and doing manipulation via force control. That required some of the force interface aspects of the KUKA in order to make that sliding maneuver happen at the beginning. Now, if we watch, if you play that again on your slides or whatever, the problem with sliding on top is there, even right there, there was some initial time where the fingers slid and the book didn't slide. So the orientation of the book was unreliable during that maneuver. There's a really nice way to get the position of the book reliable again, which is now that you're in range of the, in the nice kinematic workspace of the arm, you do this uncertainty reducing push on the side, which is just guaranteed to line up the book according to the fingers. So that's a really clever thing. And then now you're off to the side and you can pick it up in the thin orientation. So that's another example of, sort of the kind of stuff we wanted to do here. So let me actually, just so I don't switch between iPad and the screen too many times, let's actually go to that Colab. I hope you started the Colab notebook. And let me run it real quick first, but I'd actually like to go almost directly into a short breakouts here. And I want you to be able to play with it. I've got a teleop in the first cell for this. So I apologize, just because I think we're going to change it. I put some of the definitions in the second cell. So you've run the first cell to load it, but please run the second cell once just to load the function definitions. And then we're gonna run this teleop version together in a quick breakout. And I want you to think about, what's happening and how you would write a controller to do it. Okay, so I've put together a view of the Cheez-It box and a finger. It's loading a little funny. Not actually sure why it's showing me that, but you're going to see, hopefully you'll see a hand come up and the Cheez-It box. Finger false. Why is it not reloading that? I somehow failed to run this cell, I think. If I've done it right, the Cheez-It box should load once. I know that's an annoyingly big file, so it's a little slow to run, but hopefully it should load exactly once. I rewrote the contact visualization in Drake yesterday, and it's throwing a warning on me today, and I apologize. I probably shouldn't have redone that, but at least it has little arrowheads and it's bright green, and I think it helps the visualization, but it's going to throw a warning, and I'm embarrassed, and I will fix it tonight. Okay, but you get to play with this, and it's actually non-trivial to do it. So, my strategy, I'm going to orient the hand a little bit. I'm going to move it over to the side. It's updating very slowly for me. I hope it works better for you. And you'll be able to see all the contact forces between the hand and the box, between the box and the ground. You know why there's green contact forces at the four corners, because we've set up the contact geometry to have those 4 points in the corners. So the box on plane is actually doing 4 spheres on a box. Why is this working so badly? Come on. Okay, that's the one I commanded a while ago. It's also possible I screwed up the performance a little bit with the contact visualization, but hopefully not. So please play a little bit with that. And there's another version I want you to play with a little bit too, which is this, you can set point finger to be true, and that will give you a little spherical finger, which is going to be easier to think about when we write the equations. And see if you can control this. I think you can, and partly because of the way that I've authored the teleop interface. But I think just playing with it for a minute will be good. And then when you're in the breakouts, I mean, we don't have a ton of people today. I wonder if should we just do this all together now, or should we have, how many do we have? Why don't we just hang out together and unmute yourself and play with it and ask questions and tell me what you think you would do to write a controller for this, or complain that my visualization slowed things down.
By the way, Russ, there was a question from Alex on the chat.
So this was told to try to slide the book right. That wasn't a learned strategy, and even more than that, you would like to think it chose to reduce on. You know, it was just told to pick up the book, and it figured out it could reduce uncertainty by pushing that. We did not. That was just hand designed. It was told to take this strategy one after the other, and it executed. It was more about the execution. But
still pretty cool though.
The dream, oh yeah, sure. But the dream is that that should just all pop out of the algorithms. You guys teleyapping? You have to use the stop simulation button to rerun it.
Wait, oh, there's. By the way, I'm getting almost no lag on my visualization. So
Say it one more time.
I'm getting almost no lag on my visualization. So
yeah, I was having a good time with it earlier, but so thank you for saying that. I think my computer is just trying to do too many things, possibly.
My computer is having trouble with it. Well, I was able to get one movement to go through, and then after that, I can't seem to get any other movements. It seems stuck in space.
Okay.
Is adjusting the feed forward forces and torque supposed to do anything?
That's a good question. So, so I'm going to write out exactly how we wrote that. But if you were to be in contact and then adjust them, you will see the forces being applied. But there's two things happening. There's basically a PD controller on positions and a feed forward torque. So if you apply just the feed forward torque and you leave the position and it's up in the air, then it will push against your PD controller but not move very much. But if you're in contact and your PD controller is already at some steady state and then you apply your force, then you can do it. I think I'm probably just like sending contact force vector commands at a insane rate or something silly.
I feel like the only way to be able to make a controller about for this, you like have to know when it starts slipping. Like, and unless you've like categorized every material, like,
Nice.
Like, it seems impossible to me.
Good. So, right. So that is going to be one big question: is do we need to understand the coefficient of frictions, right?
Mm-hmm.
Like, what information are we allowed to have about the box is going to be a key concept today. I think there's questions about whether we're going to need to know the geometry of the box, and then the coefficient of friction, and then whether we know the inertial properties of the box. Those are all up for grabs. And I think we can do pretty well without knowing the coefficient of friction.
All right.
Even, yeah, we'll get into the details when I write the equations. If any of you have played with a position-controlled robot, this would be very hard. You would probably have to know the geometry quite precisely in order to tip this thing up. And, it would be, I think it would be nearly impossible probably to do the type of maneuver we're doing here. I'm sure you could get it to work, but it wouldn't be as clean as what we're going to be able to do. Have people been able to flip it up? That's another thing that my daughter did instantly. She wanted to play the video game I had written, apparently, and she found like 6 ways to flip it up in like no time, including ways that I think I probably need to set my time step a little lower in the simulator, because that shouldn't have happened. It was like she, right in the middle of the bin, hammered, like karate chopped the corner of the box, and it flipped up. It's like, what? But if we stay in the realm of good physics, it's not easy. Okay, so let's hear your ideas. What do you think is the right way to program that? Well, let me just finish sort of Tony's question first, just to help you understand the interface you just had, and then that might even make the question a little bit more clean. So there is some complexity in setting up that diagram, but it's not too bad, I think. The complexity comes partly from the fact that we again have 2 worlds, right? When I say worlds, I mean 2 multi-body plants. Let me find a way to be on the screen. I have one multi-body plant that has the bin, the box, and the gripper. I have a second one, which is just the robot's view of the world, which is just the gripper or the point finger. Okay. The equations of motion of the real world here are given by my manipulator equations, which I've talked a little about. These are the contact forces, right? So mass matrix, V dot is my way to write accelerations, right? It's just like Q double dot, but robust to quaternions and the like. My Coriolis terms, which happen to be linearly dependent on V. My gravity terms. This is my control inputs, which are the forces I apply. But if you think about the number of equations here, I don't have an actuator on the box, for instance, right? What's the total dimension of the state space, first of all, in this? I don't know where a button, yeah, fixed. Bin, so the total number, there's 3 DOF for the box, because I've actually, instead of having it floating around in the world in in 60, I actually put it on the plane just so we keep the dynamics clean and simple. And then I have 3 DOF for the gripper. Okay, but I don't have actuators on the box. I'm going to assume that I have actuators that can control X, Y, and theta. So U is only 3 actuators. Okay. Now, in fact, if you think about what the world's equations look like, we can actually zoom in just a little bit more. They're factored in an important way. There's the let's call it the box degrees of freedom, and then the gripper degrees of freedom. My mass matrix is actually diagonal, block diagonal like that. Okay, and I can still write my VD. I have Coriolis terms that are, the Coriolis is, this whole thing is a vector. Okay, but they're stacked. This is sort of my box one and my gripper one. Same thing, I have some gravitational torques. That's just a vector, so I can, of course, I can always write those as in this sort of stacked form. And then, you know, I have 0, 0, 0 up here, and I have U1, U2, U3 down here. That's why I needed a B matrix in order to write that in the full form. And I have almost completely independent sets of equations. Like I could just solve them one versus the other. The thing that couples them here are these contact forces, right? So I'm gonna leave those as a little bit mysterious for now, but we're gonna think about them a bit, or think about how little we have to think about them here. But that's where all the coupling comes from, okay? Now, my gripper view of the world is just this bottom set of equations. So my second multi-body plant, if you will, for the gripper, gives me these equations only, the bottom equations, because that's the only ones I actually have any reasonable access to on in the control system. So my controller is only allowed to see that bottom set of equations, but the world's simulating the whole set. Yeah. Okay. Now, how did I make the little slider interface for you to play with? If I just put sliders on U1, U2, U3, you would see nothing happen, and then you would move it, and you would see the hand accelerate off into the into Never Never Land, right? So that was not a useful teleop interface. So instead, I tried to give you a simple controller on top of that, and the standard way to do that, I could have just put a PD controller directly on the forces, but I ran through the inverse dynamics controller just so you didn't have to balance out gravity and stuff like this. Okay, so the first thing that I did is I have the multi-body plant, which has my inputs for if I have, this is X coming out, this is U coming in. I put an inverse dynamics controller here. And what does that inverse dynamics controller do? This is the one that only gets to know about the gripper. Okay, but it took those gripper equations and it tries to cancel out all the terms that you don't need to worry about. For the terms we know, let's try to cancel them out, right? So in gripper Q B dot, my equations are CG. Need a little more space on this tiny desk to be useful.
Alex wants to know what the C matrix is.
Good. So this is this together is my mass times acceleration. It's just when you get into orientation, when you get into multi-body equations, you have some terms from like the Coriolis terms and the like, which that's why we call it C, and the mass, but they go together to make up mass times acceleration on this side. And then this side I think of as being all the forces. So this is F equals ma. Yeah. Okay. So how are we going to choose U to be useful? Okay. If I command in my inverse dynamics controller U to be, if I know the model, or if I have an estimated version of the model, if I choose to command something like this, even that, okay, then let's assume that my estimates are very good for a second, and those terms actually cancel out. Then what I would get is the resulting dynamics are mg v dot equals, because this term will cancel this term, this term will cancel this term, this term will cancel this term, and it's an inverse, it's a gravity compensation, Coriolis compensation controller that results in, let's say those estimates are perfect, plus my contact forces. Okay, and in free space, the mass matrix is always invertible. That's one of the nice things about mass. So you end up with, if there's no contact, then you end up with v dot equals v dot desired. And that's a nicer interface for commanding things. You just don't have configuration dependent everything. If you had, in fact, the models that the KUKA is using internally in its controller to try to do something like this, not exactly this, we'll talk about exactly what it's doing probably Tuesday, but it is even trying to compensate friction terms. Like it knows about, it has estimates of joint friction, and it will try to cancel those out too. Okay, but basically take all of the Cruft in your equations and try to cancel out everything you think you know and give yourself a simple set of equations. And then what we say is the v dot desired is some PD controller, which is going to be like my Q desired minus Q, the ID controller, in fact. I manually set these controller gains to just be reasonable for you. And I put sliders on just Q desired. And I set Q desired 0 dot to be 0. And this is what you're controlling. Okay. So what I've given you on those sliders here is it goes through a PID controller into an inverse dynamics controller, into the plant. And then what did I do with the forces here? So I actually, it's a little bit more subtle than this. I allowed you to also put sliders on the force here, if you want to command that directly. There are feedback loops that each of those controllers need to know the current state of the plant in order to do that. Okay, so that's a reasonable thing to teleop. Is it a good thing to control this flip up? Like, how would you then choose QD or QD desired, and even Q dot desired in order to flip up the box? Like, what do you think? I mean, just what if I said, you have a quiz right now and you must program this box to flip up, and your grade depends on it. Like, what would you do in the next 10 minutes? How would you try to program it? Come on.
Well, I was gonna say I'd probably figure out a bunch of set points in the configuration space, like in Q, and then just let it follow it with the PD controller, PID controller.
And how would you pick those set points?
Trial and error. I only have 10 minutes, and
That's fair. That's fair. But so would the set points be where you want the hand to be?
If you want force, you should make it like somewhat. If you when you're trying to like get to the box, it should be somewhat inside the box.
Exactly right. So there is a solution that can achieve this with those sliders, and it depends on how strong KP and KD and KI. But let's just say KP is the easiest one to think about. You're effectively putting a spring between your current configuration and the desired configuration. And if you want to apply a force, then what you should do is put the rest part of that spring inside the box, and it'll try to pull yourself in. Okay, and that is actually an interesting way to think about how to flip these boxes up, and we'll talk about it. There's a sort of a the impedance control view of the world is that you should actually program the compliant interaction between your robot and the world, and treat the world as roughly unknown. Okay, and that is equivalent. That is sort of what the interface we're giving you here is. But that's a pretty indirect way to think about the forces you're applying. And if we know a little bit about the friction cones and things like that, my claim is that as a programmer, we can actually use the force sliders directly and do a pretty darn good job. So let's think about that first, and then we'll make Neville happy next and do the impedance control version after. Okay. Neville Hogan in mechanical engineering is the father of impedance control. So I've lost me. So I want you to start thinking about forces, and you have that. Hopefully, you still have that demo up, and hopefully, it worked a little bit, and I didn't screw it up too much. But here's a specific, quick check yourself question. So I've got the box on the ground, and let's say I take either hand. I don't care if it's the point finger or the gripper. Can you do what Giaggi did in the book video? Okay, so you have contact force vectors. I made them nice and bright green now. So you have contact force vectors coming up from the corners. You're going to have a new contact force between this object and the box. And I'm asking, can you slide the box sideways? You can try it, and you can think about it, but I want to know if it's possible. And you can speak about it. What do you think?
I think it probably depends on which interface has more friction.
Good. And is there a simple rule for how those coefficients need to be balanced?
Sorry, say it one more time.
Is there a simple threshold of sort of, is there a simple relationship between what those frictions have to be?
Oh, yeah, I guess that the coefficient of static friction on the top one should be higher than the one on the bottom.
Yeah, as long as it's even a little bit higher, we should be able to potentially move it, right? The coefficients of static friction. So let's just make sure it's I think the thing that's potentially, confusing about that is that we have multiple force vectors. We're representing our contact with the table with, right now in my picture 2, you saw in the simulation 4, really it's a pressure distribution if they had a real box, right? Does that matter? Like, does it matter that I got 4 vectors versus two vectors or whatever, forces add. They enter the equations linearly, and the coefficients of friction are linear constraints on those forces. So it actually doesn't matter. I could have the integral, I could have the force, as long as force balance has been maintained, all those things work themselves out. So how do you think about that? So let me just start, let me call this F1, F2, F gripper, okay? So I think in force balance, if I've just pushed down, then I have that F1 in the world Z direction plus F2 in the world X direction had better equal negative mg, I guess, plus or minus, I guess. If I think of this is a negative force. The way I've drawn it is already a negative force, just to keep it all in the same coordinate system. Minus F2 of W Z. Everything's in Z. Yeah? And I have rules that say that the friction cone for F1 WZ looks like this. There's absolute values because it's on both sides, but in the case where it's positive, I can, and I'm just thinking about one direction. Let's just think about the positive only case. And I have the same thing true of F2 in the Z direction. And that implies that the sum of these things must also be less than or equal to the sum of those of the horizontal forces, right? And I could have had that be an integral over the surface too. There's those things being linear means that that's okay. It really only matters what's the total normal force that I'm getting from accumulated and what's the total friction force that's possible given the coefficient of friction. Okay, now let's be a little bit more careful. Like Tony said, we have two coefficients of friction. We have a coefficient of static friction. Well, we have two static coefficients of friction. We'll call this like the box on bin static friction. And then the gripper. Now it's interesting because the static friction, all these friction coefficients, first of all, they're all kind of, just a super approximation anyways. But even as an approximation, they are always a property of pairs of objects, right? So it's the way the material on box 1 or whatever interacts with the material on box 2. And we normally cheat that in simulation, right? We say in my SDF file, I've got a coefficient of friction for this object. I've got an SDF file with a coefficient of this other. And there's always some little black magic behind the scenes saying, I'm going to somehow average between these two coefficients of friction to somehow make a rule that combines the two coefficients of friction into one for every pair, just because you don't want to enumerate every pair of possible coefficients of friction in your definition files. But in practice, it is actually a feature of the pair. Now, if you watched, and if I had my better setup, I would go back and if you've got the slides up, go back and watch Giagi's video again, and you'll see that that the gripper has like duct tape. It's like a high friction tape basically on the fingertips, and that's how it worked, right? So it is in fact only possible when the coefficient, if I start, I think you can see from these equations here, if I start trying to apply a horizontal force here, right? The finger will slip. If the coefficients are the same, the finger will start sliding at the same moment this was sliding. So it will not you know, well, I guess you're right on the line of being able to do it. But if your coefficient of friction is bigger here, then there is a solution where the horizontal force here is still inside the friction cone on the top, and it's outside the friction cone here, and you'll get your nice sliding contact. Okay, but because that's even the static versus you know, dynamic friction, if you noticed actually, the book, the hand came down, it slid a little bit, and then it kind of caught on something, and probably a little bump in there, and then it was good. And that was unreliable enough that we had to do the extra work. Okay, so let's try to do the box flip up now, thinking about forces. Okay, so first off, I have my box on the table. I've got my wall over here. And let's think about a point finger. Made a nice red point finger. And I'll start it at a reasonable horizontal position. There's some really nice things about force control. And in fact, even in walking research, we tend to use force control quite a bit. In walking research, like if your walking robot is force capable, you will tend to see people do effectively position control mode, which would be you know, using the PD controller and like the inverse dynamics controller I just said, while the robot's leg is swinging. I know you can't see my leg, but imagine my leg is swinging, and I want to have my foot in a certain position in space. So you would put the swinging leg in a mostly position control mode. But at the moment before you start putting your foot down, a robot like a Boston Dynamics robot that can do force control or any of these, they tend to go into a force control mode. Okay, and there's a reason for that we can see here immediately. So as I start programming my force control only, I'm going to lop off the inverse dynamics and just command forces directly first, just to understand that. What happens if I apply just a constant force on my fingertip directly to the right? Well, okay, I could tell you what happens because I did that first and I forgot, and I was like, why is my finger ending up down here? And then I realized I have to add gravity plus a constant force. Okay, but simplest controller you can imagine, you know, cancel out gravity and then add a constant force. And let's just say hold it on for 1 second. What happens to the, you know, to the system? Right, the finger starts accelerating this way. It will accelerate at a constant speed. So if you're too far away, you could, you know, you could hit escape velocity or something, but you don't want to. So you don't want to start this too far away. But if you're relatively close to your contact, then this thing's just going to accelerate until it hits this. If the force is enough in the horizontal plane to overcome the static friction of this, then the box will move. You can find forces that the impact is enough to start it moving, but the force is not enough to keep it moving, and it will come to rest. But if you put yourself sufficiently above that, then my simplest controller, which is just execute a constant horizontal force plus gravity, will actually come into contact on here, generate a constant resistive force, and slide the block over to the edge. Boom. Constant force, right? That's one of the great things. And you can imagine if you're a robot foot, right? And you have some noisy measurements of the ground, and your robot's foot is coming down on the ground, right? Then saying I want to be down with some amount of force is a much more robust way to be less sensitive to the geometry of the ground to make contact. In the DRC finals, we got super paranoid about, so one of the 4 test things was like canted in a weird way. It was just like the pavement was old or whatever, and we found that out the night before we got there. We're like, that's not flat, you know, what are we gonna do about that? So we went in and we changed our thresholds a little bit on our when we turned on the force control, basically. And we all, I think anybody on the team would describe the robot as being stompy that day, but it didn't fall down, right? So I mean, this is real. This really adds robustness. It kind of like clumped itself down a bunch, but mostly didn't fall down. Okay, now the more interesting part is how do we rotate it up? Okay, so my claim is that a successful strategy that using my, all my constraints on my daughter's instincts would be to get the box into this sort of configuration where it's resting, it's applying forces only in this top corner, right? And I have a finger here that's applying some forces here to be determined, okay? And basically I need to push and cause a rotation while maintaining force on the box in order to pitch that box up, okay? Now, if you think about everything that needs to happen, at some point, of course, that's not going to be possible if the box gets vertical enough. Then the force needed to push into this will be outside the friction cone up here, and the finger is going to slide off. Success in a quasi-static sense will depend on whether our center of mass moves past this point before that happens. Is that fair? I'm being very sloppy with my, right? But at some point, my finger's not going to be able to apply meaningful force without basically stopping and moving to some new place. And since this is actually, I drew it a bit, let me draw it a little bit more carefully because of that. It's actually not on the ground here. It'll be up in the air. When my finger gives up, because it's outside the friction cone, this box will fall. If the center of mass, you can think about the key dynamics here being dependent on this angle. If my center of mass here is to the side, it will fall and tend to tip into the configuration we want. If the center of mass was still over here, then it will tip over this way. Okay, so success means having a coefficient of friction and a good enough controller, but a coefficient of friction between your finger and the box that is sufficient to achieve that configuration on the box. It makes me wonder. I wonder if the way that my daughter did it, the way that I didn't want her to do it, I guess that would be better, right? Well, it seems like it should be worse. Right, if the box was thinner in that direction, it should be harder to achieve that. So maybe she was wrong. Okay, how are we going to write a controller to achieve this? My claim is that with position control, even with impedance control, there might be some natural strategies. I'm gonna show, thinking about having a very soft spring and having a remote center of compliance is actually a really cool idea that we'll talk about. But for now, let's just think about direct force control. What are the rules of the game here that allow me to move that box up? Okay. After we've moved, my controller is actually pushed to the right with force 4 for the first 1 second. Okay. After that, I'm going to enter this next controller mode, which is start balancing the forces. So I'm going to actually write a quadratic program where I'm going to define my decision variables here as the force. Let me call this point A with the coordinate frame like this. And this is my contact point C with the coordinate frame like this. And I'm going to just design I can use whichever decision variables I want or in whichever frame I want, but I'm going to go ahead and try to solve for both the force on the wall and the force at the box. I'll write it in world coordinates, but we're going to put constraints both on world and relative coordinates. Okay, I'll leave the objective for a moment. And of course, the first constraints are my friction cone constraints. So I'm going to say that now what right do I have to say that? If I just assume, if I only make the assumption that the normal is coming out of the wall, then that's, I think, since I know the bin, a reasonable assumption. It demands nothing of my perception system. So I can just write that as, in this case, world Z is less than, I'm sorry, world X, no, world Z is less than FA world X. And actually the -2, but that one won't be active. Now, the friction cone in the other one is, I'm going to write it in the contact frame. So I do need to be able to change frames between the world and the contact frame in order to write this controller. That rotation matrix depends on the orientation of the box. So I am going to ask perception for the orientation of the box. And it's not going to be very sensitive to it, but we are going to ask. I think that one's kind of reasonable. You could try to estimate it. If you have a good force sensor, a directional force sensor at the tip, you could try to estimate the, or even geometry sensor at the tip. You could try to estimate it with a local sensor, but I think this one we'll just assume we have from perception. And then in the contact frame, we can write the coefficients of friction easily. Okay, what else do we need to do? Somehow we know we're going to be in any quasi-static case here, we're going to be in force balance. So I need to relate the two force vectors. So I'm going to go ahead and write that FA WX is negative of FC WX. Right, it puts that as constraint there. I could add, and I did in the code, but I was actually realizing that I probably don't even need it. I could say that the sum of these forces is greater than or equal to negative mg. I'd like to balance, but I suspect in order to accomplish the other task, that's going to be trivially true. So that would not be an active constraint. But it doesn't hurt to have that in there. Say we're going to allow this thing to, we're not going to let it slip out immediately. And then the interesting thing, so this sort of defines a reasonable set of forces that will help hold me in some sort of quasi-static balance. But now I still have some freedom to try to rotate the finger. So the interesting thing is, well, how do you choose basically the normal force on the finger? Okay, so I think it's natural to choose that sort of in the coordinate frame of the box there. So we have some contact point. I did not carefully position it next to the corner. I just said it's a little bit under the corner. That's probably fine. I want to, again, think about not having a heavy dependence on the geometry of the box because I want my same controller to work even if perception is noisy or whatever. So what's the total moment? What are the dynamics of reorientation for this box? Well, again, I've got mg working against me. I've got these normal forces. Whatever this force is, it doesn't contribute to the orientation around the box. But I could write some equations of motion for that orientation around the box, which is going to have some moment of inertia corresponding to the mass, okay? And then it's going to have some contribution from my gravity vector, which I'll summarize with P to my center of mass cross mg. But we're going to ignore it. Don't worry. I just want you to know that it's happening. Okay. So I don't need to know the mass necessarily, except for this constraint, which I probably didn't need. Okay. Now what's going to happen here? So there are two components here. If I'm applying some force like this, I have the normal component, which is my my normal component in this coordinate system. I'm going to just assume that that's small, and we're going to call it a slop term, okay? And what I care about here is designing this controller so that it roughly servos my system up into the desired orientation. So I'm going to say this is, it's basically almost providing a pure moment, but it's some length to that thing times f of c cx plus some slop terms, okay? And I'm just going to put a PD controller on f of cx and let it overcome all that slop terms, okay? So let's say that f of cx is just some new kp theta desired minus theta plus kd theta dot, minus theta dot there. Okay, and I'm going to just prescribe this to be like a simple ramp. I'm going to go straight, apply constant force for the first 1 second, and then just start setting theta d to be moving up. I think I did 0.5 times time minus 1, right? So I started at time 1, and then I just started moving theta up. Okay, this works fine. This is like such a simple controller, and it's going to do everything we want. Okay, it's going to maintain contact force on the, it's going to maintain that force balance. It's going to start moving things up, and it'll accomplish the task. Let's see. It's the second cell on your notebook if you want to just run it yourself. Let's hope it works well for me here, but it's super satisfying. Except for that arc sign warning. Now, I did continue to apply force after the box went up, and so the finger shot off to infinity. That could be cleaned up. But let me run it again, because the contact forces are supposed to show during the middle of the thing. And I actually have it play at a comically slow speed, just so you can watch the force balance as it goes. There we go. Okay, here we go, watch. Whoa. Even that was too fast. But if you want, you can, unfortunately the forces don't get stored in my recording yet, but you can watch it happen. Beautiful. Okay, contact forces are balanced on that corner. It does hang on that corner, and then it does use a little bit of momentum, I think, to get over that top and sticks the landing. Okay. Force control is a good thing, all right, and we hadn't touched it yet. Now, let me foreshadow the impedance control version of it, but then I want to tell you how we would do this if the whole arm was attached. Is actually pretty simple and pretty important. Okay,
well,
so yeah.
Sorry, before we go there, Antonia had a question.
Yeah, good. How can you tell from inspection? Why do I not need that constraint? Why do I think I not need that constraint? I don't know if I need it, but because it depends on how sloppy my slop terms are. But I think the position control, the position control is basically going to. Okay, my guess is, now that you're asking me to think about it, my guess is that at the beginning of time, it is actually active as it lifts, but the ground could have been compensating for me. And then once my desired theta moves beyond the threshold, which would compensate for gravity, then the PD control term alone would achieve the trivial greater than mg constraint. That is we should look at it actually. We have everything we need to see if that constraint is active. But yeah, so when theta desired, because it's an error-driven controller, so when the theta desired is actually at theta at the beginning, then that's not going to be doing enough to resist the forces, so that constraint is probably active, and then as it moves forward, it would not be. That's my guess. The reason I revisited it in my head was because there is an important question of how much have we assumed we know about the object, right? If I can say that I don't need to know the mass, then that's a pretty good thing. And in general, I think even if I were to double the mass or whatever, it would be pretty robust to that. In fact, to make it more conservative and to show that I was not using the friction very much, I just assumed I had less friction than I actually do. And that puts it in a more conservative regime. It'll push a little bit harder. It might actually compress the cracker box. If I were to set that to 0.1, it might squeeze the heck out of the cracker box, and that wouldn't be good. But in this way, both because I want to pretend that the system was noisy and I didn't know it, but also because actually the full multi-body implementation of friction and everything has details that mean it's not in quasi-static all the time. And if I were to put those exactly at 1, it would actually slide and come out too early. Okay, so I mean, the thing that you were doing that you might have done was probably harder to think about, but maybe not so different than this. Right, when I did it in my teleop, the first thing I would drive the desired position somewhere into contact here. That produced some reasonable force. Okay, and then I started driving the desired position of this. So you can think about this as a spring pulling my finger, right? And at some point, this will start moving up as I pull this up. And now the magical thing is, as this finger starts moving here and here and here, it will actually pull back down also. So a fairly simple desired trajectory in the virtual force frame, if you will, could also achieve the task. And I'm going to try to talk about that a little bit more geometrically, make sure you understand the conditions for that next time. And that is sort of at the heart of impedance control, of trying to program the virtual interactions between your force, your unknown forces and your robot.
Oh, Russ, are we supposed to be seeing your iPad?
Oh crap! Thank you.
No, Alex pointed it out. So.
Yeah. Thank you, Alex. Yes. So now you just see scribbles, but I have a force here as I dragged my virtual force inside here, thinking of having a spring like this. And then as I raised it up, I have a spring here. Eventually it will cause enough vertical force that the brick will start rotating up. And then because this point still stays inside the body, once it starts moving up, it will actually snap in sort of a nice way and mostly keep contact. But the thresholds on that are much harder to think about, and they're hidden in some games, as is. I will give you the remote center compliance version of it, I think, next Tuesday. Okay. It turns out at first blush, it's actually not too hard to implement that extra, that type of controller on the KUKA. If we were to, certainly in simulation, if we put that on and wanted to achieve the same thing with the commands running through the joint commands instead of the floating base commands, I think we can do the same thing. Let's just make sure we think about the different options here. I think the best case on a real robot is that you have actually a force sensor at the point of contact, okay? People are working on that. And I think getting more tactile sensors, we're gonna have a guest lecture on that later in the term, having more tactile sensors. And I know some folks in Berto's group are working on this. You know, I think can be very enabling because everything's better if you can sense the force directly at the point of contact. Once you do that, then you can overcome a lot of any modeling errors of your gripper, of your arm, of your friction and stuff like this, as long as you know incrementally how a torque in the joints affects the forces at the end, you can then close a servo loop to command your desired forces, right? We rarely have that so far. People tend to have, if for trying to do these kind of tasks, a lot of robots don't have them at all. But if you're taking a robot and trying to do a force-based task, then you will often have at the end of your arm and before your wrist inserted a relatively expensive 6x force torque sensor. So if that is the case, then it's up to you to either invert the any effects that come from the gripper, or just pretend that they're small relative to the interaction forces. Is often sort of often brushed under the rug. Okay, or if you must, then you can have a complete model-based approach where you basically you're just using the equations of motion and inferring from joint sensors, even accelerations, potentially, you can estimate the forces that must be happening because of the relationship in the equations of motion, right? You can estimate those with measurements of Q, V, and V dot. Yikes, we try to avoid that, okay? The other things you can do are you can try to command a U that regulates this sort of directly, okay? So if, for instance, you're in quasi-static like this, the equations get a lot simpler. You can ignore this side of the equation. Just think about your force balance. And if I'm in my fully actuated, because I'm just using the gripper, I'll leave the B off so I can command everything. Then this gets us back to what we were doing actually on the fingers, right? Was writing U to cancel mg plus the commanded force. If we are able to subtract out this model directly in the low acceleration, low velocity regime, then we can actually just use our joint torques to connect to the force. And you can see from this relationship, then actually the commands you need to send should look like you want to do actually, if let's take the single force case, you really want to do something like this, so that when you put the whole thing together, you're left with this canceling this, and U going through the Jacobian transpose to setting F desired roughly equal to F contact, your desired contact. Okay, so inverse dynamics control, model-based control actually can do some amount of force control. In practice, what we tend to do with the KUKA, for instance, the KUKA push in the book, it was a combination of the joint of the end effector control. So we have KP plus KD, whatever, for the joints. We planned a motion to put the hand into contact, and then we added, just like I said way back in the beginning, what you did in your teleop. We just used this interface. We said everything's going well here up until we got into contact. And then we just added a little, not with sliders, of course, but with a controller that added force directly in as just a feed forward extra torque to then regulate the force on the book and push the thing sideways. Good. I hope that's, I hope that gets you thinking that manipulation is more than grasping. I think I don't have enough time to do the impedance control now. So maybe I'll take questions, of course, but let me end a little early, and I'll do the impedance control version of it on Tuesday. What other questions does anybody have?
You teach 6832, right?
Yeah.
Does it go more into this? Because this seems interesting, but I also feel like a lot of this is like very overwhelming, like to really internalize right now.
That's good feedback. That's actually kind of the feedback I'm asking on the question here too. So, of course, yes, it does go into a little bit more details, but tell me also what would help at this level? What are the things that feel overwhelming?
I think right now, I don't have a sort of understanding of the physics as much. Like, so when you wrote out like the equations of like the mass matrix, I still don't entirely even know what that looks like. The Coriolis, like all that out. Like I sort of in the abstract understand what that's saying.
Yes.
But I don't know how to like use it.
Yeah, good.
I'm not sure if that's the case for me.
No, I think you're.
I'm
sure you're not alone in that. So thank you for saying it. It's always a balance to try to think about how much time to spend on it. My plan for this class was to basically give 2 lectures that required, this one and the next one that taught us a little bit more about what was happening inside the robot level in order to control forces. And you're right, underactuated talks more about it, but in the special case where B, where you don't have enough actuators, that's what makes it underactuated, when B is low rank, because that's where everything gets more interesting. But I
mean, even if you just like had in the textbook just a small like write up on like what these matrices look like.
Good. I do actually. Well, there's a link to the underactuated appendix in that actually I think even Meng included one of them, but I would even link to the appendix version of that. But yeah, I think we can definitely give you some references to help. And thank you for saying that. I think the thing I want you to come away with is that there is a big difference between what we can do on the robot side. Roughly speaking, for a robotic arm of the type we're working on, you can exploit your knowledge of the arm and the relatively large capacity of the actuators to impose almost any dynamics you want on the hand.
Mm-hmm.
And my goal for these 2 lectures is to basically say, you can ignore the arm from here on out, and that we can basically impose the dynamics at the hand that we want with the world. So that floating hand assumption the reason I'm sort of okay simulating floating hands is because we can actually make that true with, you have to do your due diligence to understand, how to get there and what the limitations of those controllers are. But roughly speaking, we can impose dynamics on the hand. And so the interesting thing then becomes the dynamics between the hand and the world, and the contact forces and grasp planning or non-prehensile.
Okay. Also, sorry, I don't want to talk all the time, but I was curious. For the theta controller, for like when you're actually trying to flip it up, so I would imagine you're trying to control for the angle of the box, not like where the hand is, because you don't really care where the hand is if you don't have the box still. So like, how do you make sure that, is it just in perception that you're like, okay, we still have the box, we still have the box, we still have the box?
Good. Okay, so yeah, I think a super important point of this controller that we wrote is that it does not care at all where the hand is, which that actually, if you were to apply this controller with no other modifications with the gripper instead of the point finger, then, and I did, and it runs into the box on the other side of the finger and then slips off, right? But so it is, I like that it is naive about the rest of the, that's sort of a strength, is that it doesn't have to know anything about, about the gripper or whatever, but it does run into limitations like that. So what am I asking for the perception system? I'm just asking for the orientation of the box. I do have some numbers in there that are a rough weight of the box, but I think we could see if we explored it that I could like multiply those by 0.5 in either direction, and it would probably be fine. The controller would still work.
All right.
An uncertainty analysis would be the next level of sort of maturity that we could do here. Would be to say how robust is this controller to variations in the coefficient of friction and in the few things we've asked for from perception. Even theta, I think, would be the angle of the box. I think would be pretty robust to that.
So you do hard code like how much force is necessary there in order to like maintain your grip. You just the only control part is like where you are in the angle. Is that true? I don't know.
What I did is I made a conservative approximation of the friction cones, and thinking about the angle that I'm pushing, I decided vectors that would stay inside the friction cone, that would pull up enough and rotate enough so that so that basically I didn't lose contact with the wall. That was the major thing, was make sure that I stay inside the friction cone of the wall while I slowly push up and around with the other side of the box.
That was just an optimization.
The reason it's an optimization is just to handle it's almost linear equations, but because these are inequalities, think of it as just solving a set of linear equations under inequality constraints.
Okay.
And just like in the Jacobian case, if it was unconstrained, we could solve linear equations, but in the constrained case, it's just easier to solve a quadratic program.
Okay, that makes sense. Thanks.
Could I ask how much of the TRI book example was, how much of it was automated and how much was scripted?
I mean, all the force control. So we basically consider on the KUKAs the threshold for how much your ability to measure force via the joint torque sensors. Simon, I'll tell you, 5 newtons. You can basically, like, there's a threshold right around 5 newtons that below that threshold, it's going to look like noise. You shouldn't count on it. Above that threshold, you can do reasonable control. So I think it is principled in the sense that we probably put, I think back in that day, we probably put the book in some initial configuration, and we came down roughly on it. Okay, once we were in contact, detected by the force sensors, we pushed down some threshold amount, and then drove through a prescribed trajectory, lift it up, put it down, prescribed trajectory to push it off. If I were to do one less bit of hacking and more automation, it would be to try to make that plan directly. And have it infer that, thinking about the uncertainty of the, of the possible orientations of the book, given the forces I've been applying, would it have automatically come up with the strategy to push on the side in order to reduce uncertainty? That's the obvious question that experiment begs for, and we didn't do.
Wait, so are you always assuming that you have like some way to be able to get to the object, but not like overcome the force of static friction to move it? And then once you get to the object, then you're starting to do the actual force control to like twist it around or rotate or lift it or something.
In this case, I just said I'm going to apply a constant force for 1 second.
Okay.
And if the box was twice as big, it would have just made contact and started first. That's one of the beauties of force control.
Mhm.
And I think that's the point I want to land. So,
Okay.
is that it's very insensitive to the geometry of the box. Okay, I will see everybody on